Okay, so this is lecture number 10, ECE 231, and today we're going to start a two-lecture discussion of serial port programming using a peripheral called the UART, which is the Universal Asynchronous Receiver Transmitter inside the Atmega 328P chip. And what we're after is sort of indicated in the cartoon up top. We're trying to create an instance where our little tiny microcontroller, that's indicated by the little thing that says CPU, wants to make use of the terminal capabilities of a host computer like your laptop. It wants to perhaps make use of the keyboard to send some input into the microcontroller, or more commonly, it wants to make use of the screen display capabilities of the laptop. And so this is important sometimes for displays, but it's very important for debugging, and that's the context we're going to be looking at it. So let's get into it. We're talking about the UART peripheral. Now, this is a simplified diagram. We've seen this before of our Atmega 328P microcontroller. That's in the family of AVR microcontrollers made by Microchip. AVR is the processor that's inside that, and then the difference between the different AVR chips, the Atmega 328P and the others, the difference has to do with the size and the capabilities of these and the numbers of these various peripherals. And so we talked about the I/O ports the past couple weeks, and now we're going to be looking at some of the other peripherals, namely this thing called the UART. And so this little demo here was put together to illustrate an example of how we might use this. And on the right, you can see the application, at least the hardware side of the application that I developed previously for demonstrating GPIO, a couple of buttons and a couple of LEDs. And you press the button on the left and the red LED glows. You press the button on the right, the green LED glows. But what happens if you build it and you write the code and you press the button and it just doesn't glow? How do you go about debugging a system like this? And it can be complicated because you can have problems on the software side, you can have problems on the hardware side, you can have problems on the hardware software interface. I mean, if you change the code and then you reflash it, did it successfully flash? Did the new code ultimately get transferred to the ROM on board the microcontroller? These are some of the things you don't know when you're trying to debug. So what I want to show you right here is how you can use the serial display capability of the laptop, of the host computer, and in particular the USB host, to just do some displays. And so let me run this little movie here. And you can see that as I press that left button, you can see what's being displayed. The left button is pressed and then the right button is pressed. This is just some text that I'm sending out from the microcontroller to the monitor. Displays like this can be helpful for debugging purposes. Now, it's not common that an embedded 8-bit system is going to actually have a big display terminal built into it. You don't usually have that with an 8-bit system. You could have some smaller displays and LEDs and things like that, but it's can be very useful to be able to do what I've just done here, where you're causing some text to be sent from the microcontroller to the big display on your laptop for diagnosing something. And so that's what we want to look at in more detail. Okay, to learn about this, we're in the area of serial communication and also UART, or sometimes called USART. I'll explain the difference. And here's a list of readings. There are a couple of tutorials that are given on SparkFun, and SparkFun is a vendor that we bought a number of the things in your kit from. Then look down at the third point there, that's the textbook. Those are the sections in the text for you to read. I'd like you to also to take a look at Chapter 20 of the Atmega 328P datasheet, and you'll find that full datasheet, all several hundred pages, on the Moodle site. The details here are pretty thick, and it's way down in the weeds kind of details, and it takes some learning to figure your way around a datasheet, but you do need practice reading a datasheet. So take a look at that, and I'll be saying some more about the datasheet as time goes on. Okay, so what we're talking about here is sending text characters between our microcontroller and a display on a what we'll call a terminal emulator on our laptop. And so since we're talking about text, let me just show you how we represent text on the microcontroller. So let's take the letter A. And if I take A and I put it in single quotes, that means that we're dealing with an object that is a piece of text. Now, we know that our microcontroller only thinks in bit patterns of ones and zeros. And so we've already talked about how integers are represented and how floating points are represented. Well, we actually can represent characters as a small integer of type char, that's char. And char on our machine is an 8-bit representation. It's an 8-bit integer. And this data type is used to represent characters in what's called ASCII. ASCII stands for the American Standard Code for Information Exchange. So this is it's a standard way of representing characters using either a 7 or an 8-bit word. Now, why 7 or 8 bits? Well, first of all, the character A is represented by the number 65 in decimal, which would be the number 41 in hexadecimal, or this pattern of ones and zeros in binary. And if you look over at this table here, you'll find this is a standard table. So anytime we want to represent A in ASCII, we would represent it with one of those values, with decimal 65 or hexadecimal 41, or the corresponding binary pattern. And if we wanted to represent lowercase a, we could find that on this table. Okay, it's represented by number 97. So that's in 7-bit ASCII. Now, why is it 7-bit? Well, if you look at the total number of things on this standard table, they go from 0 up to 127. 127 different things that we want to represent with this code. So 0 to 127, there are 128 different elements, 128 ASCII symbols. Now, these symbols include the letters capital A through Z, lowercase a through Z, the numbers 0 through 9, and a number of other characters that are both printable and non-printable. Non-printable characters meaning things that sound bells, things like that. All of these characters can be represented in text with type char, char, and they only occupy 7 bits of information to represent them because there are 128 of them. And 2 to the 7th is 128. So if we have 7 bits and we look at all the possible combinations of 7 bits between all zeros and all ones, there are 128 of them. So using a 1-byte word, which is the standard thinking element inside our 8-bit machine, that's an 8-bit word. It turns out we only need to use 7 of those bits to represent standard ASCII. Well, what about that last bit? Should we just make it a 0? Should we just make it a 1? Should we waste it? Sometimes that bit can be used for something called error checking, which we're not going to get into. Other times that bit can be used to represent extended ASCII. There's all of the 7-bit ASCII that we just talked about, plus an extended set of characters, if you look at them here, and they include various symbols to represent letters in other alphabets, for example, with accents on them. They can represent letters of the Greek alphabet. You can see some of those over on this side. So the point here is that we have standard ASCII and extended ASCII using 7 or 8 bits respectively. And I just bring this point out because when we're going to start to look at how to communicate data between one device and another, we'll just have to agree. Are we dealing with 7-bit ASCII or 8-bit ASCII? Okay, and that'll be part of the protocol that we agree upon in order to send data between one machine and another. Now, there are many ways of communicating between 2 devices. I'm just going to look at 3 different types of communication. This is by no means an exhaustive list of all the ways to communicate, but we're going to look at parallel communication, and then we're going to look at serial communication, both synchronous and asynchronous. Okay, and you probably know that synchronous means that there's a common time base or a common clock that's shared, and asynchronous means without reference to a common clock. And it looks like I have a little typo that should be there, asynchronous. Okay, and you've experienced over the past couple of years synchronous learning, where everyone is viewing a class at the same time, and then asynchronous learning, where I might record this lecture and you view it later on, right? And you're viewing that independent of the real-time clock. You're viewing that at your own clock. Okay, so let's take a look at synchronous parallel communication. So parallel communication, that's clocked. And so here's the idea. Suppose that we want to send out the letter A, just a simple character A, and I have a transmitter that's going to send that out, and I want to send that over to this should say receiver. Right? We want the receiver to get the letter A, and we're going to do that with parallel communication. By that, we just mean, since we have 8 bits, well, let's agree, we would have to agree that we're going to be using the 8-bit extended ASCII as opposed to 7-bit. That's just a protocol agreement between the transmitter and receiver. So once we've established that, we're going to configure a whole bunch of wires. That's the hardware part of the agreement. And there will be 8 data lines, 1 for each bit. And there's also a clock that we have to send out. And so the agreement that we would have between us is that we're going to transfer data associated with the clock. It could be on the rising edge or the falling edge of the clock. And we're going to have a hardware configuration where we're going to be sharing 8 wires, 1 for each bit position. And we're going to share the clock, and we're going to share the ground between the 2 devices. And I made a point here of saying, don't forget to connect the grounds. Some drawings don't actually show the grounds. And sometimes, particularly when people are beginners at this, they'll hook things up and they'll forget to connect the grounds between 2 different machines. And you don't want to do that because, these bits are going to be sent out 1 or 0. A 1 is going to be a voltage relative to ground, might be 5 volts, might be a different value. And a 0 would be a different voltage relative to ground, might be 0, might be a different value. And they're all relative to ground. So you have to share that ground wire, between these two terminals here. Actually, to do that right, I should show that as a black wire. That's the standard that we would use for representing ground. Okay. So that's how we would configure it. We would from somewhere within the memory, the data bus on our transmitter, we would grab the 8 bits corresponding to a byte that represents the letter A. And we're not looking at how we're actually grabbing that, but the idea is we would take all of those bits and we would load them into this output register, which would then send them across to the receiver. It would then grab all those bits and it would then, one way or another, communicate them with however it's going to consume those bits on the other end. The point here is it's parallel communication because we have 1 physical wire for each bit. So the hardware here, you need to have a total of 10 wires. That's the 8 wires for the data. You need to have the clock and you need to have the ground. This results in fast communication because the whole byte is sent in one piece. But it requires cables with a lot of wires in them. And this is not at all practical when you're doing things over long distances. Most of the time, what we'd like to do is use a simple serial cable with just 1 wire to connect things instead of using a whole bundle of wires. And so the next mode of communication would be synchronous serial communication. And so synchronous means, again, we're sharing a clock. Serial communication means that we're going to be sending the data 1 bit at a time. And so let's first take a look at the agreement that we have to have so that the transmitter can send data and the receiving end can make sense of it. So let's agree on 7 versus 8-bit ASCII. And in this case, we're going to be using 8 bits. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we agree. both transmitter and receiver agree that we have 8 data bits. Okay, and then we might have an agreement on how we're going to use the clock. We're going to be transferring the data over 1 bit at a time. So first we'll send the least significant bit, and then the next bit, and then the next bit, and so forth. And we're sending over a clock associated with every single one of those bits. So on the rising edge, it could be the falling edge, but let's say it's the rising edge of that shared clock. We'll send over the first bit. And then the rising edge of the next clock period, we send over the next bit, and so forth until we've sent over all 8 bits. Okay, so we have to have that agreement. The hardware that we have to communicate here, we have to share between the transmitter and receiver. There's one data line and the clock, and then of course the ground that's shared in between. So far fewer wires than the parallel case, but we still have to send over the clock. The next mode that I want to show you is asynchronous serial communication, where you can send things over and special synchronization bits are added to the data. They're appended onto the data so that we don't actually have to send the clock. And that's the mode that we're going to be primarily talking about. It's asynchronous serial communication, where we have no common clock. And so again, let's assume that we want to send out the letter A. And the protocol that we will agree is we're going to use, let's say, it could be 7 or 8-bit ASCII, but let's assume we're going to be using 8-bit. Okay. Now, how do you accomplish communication if you don't have a clock? Well, the idea is that we would deliberately append and agree to append some synchronization bits onto our 8 bits of data to create a frame of data. So what we would do is we would first send a 0, that we call that a start bit. And then we would send over our 8 bits of data. And then we would add on 1 or more ones, which represent stop bits. And these are synchronization bits. And what happens is that the receiver is able to look at this frame of data, all these, this pattern of 1s and 0s that are flying toward us. And what happens is from a preceding frame of information, there would be a 1 on the line, that the line is held high. And when a new frame of data is sent, the very first thing that is sent over is a 0. That's our start bit. And so what we see is a high to low transition on the data line. And the receiver knows that a high to low transition, that marks the start of a new frame of data. So that's how it gets synchronized. And then it just starts counting bits. 1, 2, 3, 4, 5, 6, 7, 8. And then it says, okay, I'm looking for a stop bit, and that's going to represent a low to high transition, and that represents my frame. So we have our 8 bits of data that are framed in between this start and stop bit, which serve as synchronization. Okay, so we have to have in our agreement, our protocol, we have to specify how many stop synchronization bits there are. There's always going to be a start bit, but there could be 1 or 2 stop synchronization bits. There could be some parity bits that are added for error checking. It's not something that we're going to look at in all of the exercises in the course this semester, but so we'll always keep that at 0. But there could be, as part of the agreement, that there's going to be parity bits for error checking. The hardware that we would agree to, 1 data line plus a ground to share data between devices. And then very importantly, we have to agree on the data rate. We have to agree on how many bits per second we're going to be transmitting. That's also called the baud rate. And that's important because on the receiving side, it's going to turn on a clock, and it's going to set the clock to match that data rate so that the transmitter is sending data at 1 rate in bits per second. The receiver will have an internal clock that will be set up to match that because we've agreed on a data rate. And then making use of these synchronization bits, the start bit and the stop bit and the total number of bits in the frame, the receiver is going to be able to make sense of the incoming data. Okay, so what else is going on in the hardware here? We are dealing with serial data transfer. So data inside the transmitter, it lives in memory registers that are 8 bits wide. And so what we would have to have coming off of our data bus would be, we have all 8 lines coming off of our data bus. And we'd have a device called a parallel to serial converter, which is essentially a shift register. And what it's going to do is it's going to make use of a local clock, and it's going to shift out that data 1 bit at a time. So it starts out with that 8-bit word, and then it shifts out. It would first shift out or send out or transmit the start bit, and then the least significant bit, and so forth on up to the end of the data frame. And then on the receiving end, that serial data stream is coming in, and a serial to parallel converter is going to take that data, and it's going to turn that back from a bit stream into an 8-bit word, which would then get sent into the data bus, or it would get consumed by whatever the application is on the receiving end. Okay. So in this picture, we're really only looking at one-way communication. We're getting toward the basics of how we do serial communication. You've probably heard of serial, about serial ports. You may have heard about RS-232. This is quite similar to what happens in RS-232, the difference being the voltages. In our device, we're using TTL, that is, a 0 is sent as 0 volts and a 1 is sent as 5 volts. In RS-232, those voltages are just sent as something other than 0 and 5. But let me just show you how we would make this two-way communication. Instead of just here transmitting from the left and receiving on the right, how do we sort of evolve this picture into a scheme that can both transmit and receive even simultaneously? Okay. Well, here's the picture. So focus on the left. This would be device A, such as the microcontroller, our Atmega 328P, and it has inside it a UART, a universal asynchronous receiver transmitter. Okay, UART, universal asynchronous receiver transmitter. And what it's doing is, I'm going to back up to the previous slide. It has this action going on inside it, and then on the right side, it also has this action. So it has parallel to serial converters for transmitting. It also has a serial to parallel converter for receiving and taking a serial data stream and turning that back into a parallel word. So that's what happens inside there. This is a device that needs to get fed with a clock, and so that it can clock out data at a certain protocol, at a certain agreement, right? So you program one of these devices by telling it how many ASCII bits you want, how many stop bits you want, whether to use a parity bit. There's also the agreement here for hooking it up to something else, the number of hardware wires. It will be 2 wires in this case, one for transmit, one receive, and one for ground. And you also program it with a certain data rate, number of bits per second. That's the rate at which the data gets clocked out of the shift registers. And so we have, this would be our little microcontroller. And now what we're going to do is connect it up to some other device. It could be another microcontroller. It could be a printer. It could be the USB port on your laptop, or it could be some other device. The point is, without having to know the details of how that other device works, what we would agree with that device is we're going to be sending it over data following a protocol, certain number of ASCII data bits, certain number of stop bits, certain parity bits, and a certain data rate. And we agree that this is 3-wire communication. We're going to be sharing a transmitter line, a receive line, and a ground line. So with that 3-wire hardware configuration and this agreement to send data out packetized in this way per this protocol at this rate, that's how we accomplish 2-way asynchronous communication. And we don't need to provide a clock in between. We just have to have the 3 wires to connect the 2 devices. Okay. So now let's start to get into what this looks like on your device. Okay, it looks like I have another typo here that should say frequently. So inside your Atmega 328P, if you look at this architectural drawing on the left, which you'll see on the data sheet, one of the many peripherals in here is called UART Zero. Okay, now USART stands for Universal Synchronous Asynchronous Receiver Transmitter. So this is a device that can support serial communication using both synchronous mode, meaning you share a clock, or asynchronous mode, which is the most recent one we discussed, where you don't need to share a clock. And the synchronous mode is used less frequently. It's the asynchronous mode that's used most frequently. So this device can function as a USART, or it can function as a UART. At least that's what we're going to call it here, for Universal Asynchronous Receiver Transmitter. So we won't use the S in there. We'll be calling it a UART. Okay, why is it called USART Zero in here? Some AVR microcontrollers have one USART UART peripheral in them. Some have more. Some don't have any. There are big there are big AVR chips that have as many as 3 USART UART peripherals in them. And so on the data sheet, it just numbers them 0, 1, and 2. That's how in 8-bit microcontroller speak, we tend to number things. We tend to number everything starting with 0. Right, so if we have n of them, then we would count 0, 1, 2 on up through n-1. And this applies to everything. If you think about the numbers of the port pins, there are 8 pins in port D. They're numbered PD0 through PD7. If you think about how we index an array, we actually start with element 0 and go up through element n-1. So I just that's a bit of a sideline, but I just wanted to sort of remind you that in embedded programming, we tend to count things starting from 0. So when the data sheet shows USART 0, it just means USART. No, it's the first of n USARTs that are built into that peripheral, and we just happen to have 1 on this device. Okay. And over on the right side, you can actually see the 2 physical pins that are associated with that UART. Those are just data pins, RXD for receive data and TXD for transmit data. And one thing I'll note about this is, we've previously made use of those pins as PD0 and PD1, 2 of the 8 pins associated with port D. Well, it turns out many of the pins on this chip will do double, triple, even quadruple duty. There are multiple functions associated with them. And so what we're going to be doing is drawing out explicitly 2 of the functions of pins 2 and 3 on the chip. Those pins can be used as PD0 and PD1, or they can be used as the receiver and transmitters associated with the UART once we enable the UART. And so the key here is whether or not the UART is enabled. If it's disabled, it's essentially powered down. And if it's enabled, then this part of the chip is actually up and running. And there is a potential issue for contention, or that is conflict between the port D functions for pins 0 and 1 and the serial communication functions if we're trying to do both at the same time. And we'll encounter that, and I'll walk you through that in a couple weeks. So let's take a look at how we would actually do the physical configuration here. How do we actually hook this thing up so that we have serial communication using our UART to our laptop? And let's then look at the software that's involved. Okay, so the name of the game here is asynchronous serial communication between our Atmega 328P and a USB host. By that we mean our laptop. Laptops used to have serial COM ports. Now we don't find many of those these days, but they have plenty of USB ports. And so we're going to show you how to connect the chip to the USB port. Okay, so the first piece for us to talk about is the hardware, the physical communication. So we're dealing with asynchronous serial communication. So there are 3 wires, right? There's the receive wire, there's the transmit wire, and then there's the ground wire. And those are shown as the blue and the violet and the black wires there. Now, coming out of the chip, these are all serial TTL lines. So TTL just refers to voltages that a low is 0 volts and a high is 5 volts relative to ground. Now, serial TTL in itself is not compatible with USB. USB has different voltages, and it's a different standard. So what we need is a device called a serial TTL to USB converter, and that's this little device. It's a little bit bigger than a postage stamp. You have one of those inside your kit for this class, and all we do is we connect the ground wire to GND on this, and then we connect the transmitter and receiver lines. And there's a subtle point here. You have to actually cross those wires. You have to have TXD coming out of the chip. That's our TX line. Has to go into RX on this converter, and vice versa. RX going into the chip has to come out of TX on the line. It's because, you know, when you're transmitting, when you're transmitting sort of from the left, you want that to go to the receiver line on the right-hand side, and vice versa. This is not something that you have to worry about now, because we're going to be using the Arduino UNO instead of this converter, and all that wiring is taken care of internally. But in a few weeks, this will matter, and I'll remind you of it again. But if we were going ahead and hooking this up, this device has a USB mini cable. This here is a USB mini. Most devices actually have a USB micro connector, but it turns out that the mini connector is more robust. It's a sturdier connector, so it will actually survive many more cable detachments. You know, when you attach and detach the cable, if you're using USB mini, it just is more rugged than using micro. And in your kit, you should have 2 USB mini cables. Okay, and so then that just goes into the USB port on your laptop. Okay, so that's the hardware configuration. Now the software. Let's take a look at that. Well, we'll get to the part about how to configure the microcontroller, but on the host computer side, you know, on this side, what we want to do is open up a terminal window that is called a terminal emulator. What that will do is it will emulate, or you can think about it as simulate, but it's as though we have our microcomputer connected to an old-fashioned simple terminal, such as a VT100 video terminal, which is nothing other than a dumb keyboard and monitor. So it's a keyboard for sending information, and it's a monitor for displaying information. So what you're going to do is run a piece of software on your laptop that will open up a window that will serve as a terminal emulator, as though you're sitting down working with a 1970s era VT100 video terminal. Okay, and so to do that, on the Windows machine, you're going to run a piece of software called PuTTY. Now, there are a variety of terminal emulating software packages. The one that I want you to download and use, and the ones that we'll support, it's called PuTTY. It's open source. And so in the next lecture, we'll walk you through how to set that up and make use of that. If you're using a Mac, then you just use the screen command, which is a Unix command that's available within the Mac OS terminal. So once you open up your terminal, you just type screen and you specify the port that you want to connect to, and screen will be a terminal emulator application. Okay, so that's the hardware. We've talked about the software on your host computer. Now we have to set up the protocol, and this protocol that you have to set both on that terminal emulator app on the host computer, and we have to program these bits into the UART on our Atmega 328P, so that we have to set up the protocol. Okay, so we have to configure both our chip, that's the peripheral on the chip, and we have to configure our what we call the COM software. That's the terminal emulator on our host computer, right? That's the piece of code that makes it look like a dumb VT170s error terminal, okay? And you have to set them both up to the same protocol so that one can transmit data and the other one can make sense of it. So how many bits? 7 or 8. Typically it's going to be 8. Everything we do here will be 8. The baud rate, how fast that data is coming. And we're always going to use 9600 baud. We can use faster, but we're just going to keep things simple. Okay, synchronization bits, there's always one start bit, but we would specify 1 or 2 stop bits. We'll always be using 1 here. And then if there's any parity checking, typically there'd be none. On your terminal emulator software, your COM software, you may also have to specify that there's no physical handshaking. So certain other things may have to be turned off there. And we'll get into that in the next class when we actually do some demos of this. Okay, so that's how we set it all up. Now, you're using right now, instead of using a bare chip, you're using the Arduino UNO. And the Arduino UNO has a number of things built into it. That's why we're using it at this stage in the class. But it actually has a second microcontroller on the board. I mean, this is our Atmega 328P. This is the chip that we're always working with, right? That's our target. But there's yet a second microcontroller that exists on that board, and it's programmed to serve as a converter between serial and USB. And that's why you can take this device, and what it's doing is it's taking these 2 data lines that we just talked about, and it's formatting those and sending them out over USB. That's why you can just take the Arduino and just plug it right into the USB port, and it just works, right? Your laptop host knows to talk to it. It sets it up over a certain COM port, and that's all taken care of in this serial to USB converter. Now, I already talked about a couple of subtleties, but I just want to mention them again. So the serial port on the Atmega 328P, it uses PD0 and PD1 for transmit and receive, right? And that's these lines, okay? So if you're actually making use of those 2 lines over here in the lower left, if you're using those for input or output, while you're also communicating over this serial port, you will have some contention there. And that's just something that you have to be aware of, because you could be asking these pins to do 2 things simultaneously, and that can lead to errors. The other thing, though, about this is that transmit and receive have a couple of LEDs on them right here. Okay, there's an RX LED and a TX LED, and those are set, they're hardwired to the TX and RX lines. And so you may notice that these LEDs are blinking sometimes. These can actually serve as a couple of LEDs connected to PD0 and PD1 that you may want to make use of for debugging purposes at some point or another. Okay. You don't have to worry about all this stuff right now. It's just something to kind of keep in the back of your mind. And when it's important for you to know it, I'll remind you. Okay. So now how do we program the UART inside our chip? Well, we've already seen this. This is sort of the way we've built up and described it. So what I want to do is I want to get some descriptions of the subsystems inside this thing. And particularly, we want to know, how does it transmit these ASCII bytes bit by bit? Because, we know it's an 8-bit machine. So it thinks and it computes in 8-bit words. That's what an 8-bit machine does. So its basic memory building block is an 8-bit word. So we want to know, how does it grab an 8-bit word off of the data bus and then transmit that? It means clock it out bit by bit over the TX wire. And then on the receiving end, how does it take incoming data bit by bit, turn that back into a byte, and then send that back into memory? How do we configure the clock on here? There's this clock that's shown here, and how do we configure it for different baud rates? Maybe we want to use 1200 baud, that's 1200 bits per second. Maybe we want to use 115,000 bits per second. Well, whatever it is, how does that get configured? And then how do we configure the protocol? So that's the number of ASCII bits, number of stop bits, and the parity bit, etc. So first, we want to sort of get a kind of a high-level description of the system, and then we have to figure out how to code it and how to set it up. So I'll start out with this picture of a UART from Wikipedia. Now, this is an oversimplified description, but it gives you a sense. So we have our transmit register. So we may start out with our letter A, and what we want to do is get that from memory somehow and load that into a transmit register. So we put that into a transmit register, then it's going to be connected to a shift register. And you've seen shift registers in your ECE 124 course. What it'll do is it'll take each bit that comes in and it'll shift them out one bit at a time on the basis of a clock. So we have a clock. This would be our system clock. And the system that you're dealing with, the frequency of that oscillator is 16 megahertz. Now we can use different clocks to set up the time base of an Atmega 328P chip. The clock that the way the chip on the Arduino UNO is configured, it's configured to use an external clock, and there's a 16 megahertz clock that's hardwired to that, and that's on your Arduino UNO board. So it's working off of a time base of 16 megahertz. And what we have to do is sort of divide that down in a clock generator so that we can get a clock that has the baud rate that we want. We can shift those bits out one at a time at that corresponding baud rate. That happens on the transmit side. And then on the receiving side, we're going to have our bit stream coming in. That's going to get into a shift register, and that's going to get loaded into a receive register. And then ultimately, it's going to get sent someplace in memory. Now, this is an oversimplified drawing. This doesn't sort of speak to how do we configure the protocol and how do we actually set the baud rate yet. Okay, so let's look at a more detailed example. This is a fairly detailed description of the UART peripheral as specified in the Atmega 328P datasheet. Now, just look at it takes a while to get your mind around this picture. I don't want you to worry if it's not making sense to you, but I just want to sort of give you some highlights. So there's a clock generator here, and it sort of starts with our F oscillator, and that was 16 megahertz. Okay, that's also called F CPU. That's the speed at which the CPU on the chip is being clocked. And so the purpose of all of this stuff on here is to generate a clock at the baud rate that we need. Then we have the transmitter, okay? And the transmitter is going to take our ASCII byte that we want to send out. We're going to put that into a register called UDR, which is our UART data register. Then it's going to go into a shift register, and then it's just going to get sent out. Along the way, there's a thing called a parity generator, which would be for error checking. We're not going to make use of that. On the receiving side, we have a serial stream of data coming in. We have various things for parity checking, data recovery. We'll ignore that. Basically, that data goes into a receive shift register, and then it gets clocked back into another register called the UART data register where it gets received. And just notice that there's something called USCRNA. That's the UART control and status register, N for UART Zero. And then we also have register B and register C. Those are used for configuring the protocol. Okay, so now this is a very high level picture, and I glossed over a lot of the detail, but I just wanted you to have a sense of how the data sheet speaks to this. On the next slide, I want to show you how your textbook describes the UART. So this will be the third description of the UART. First, we looked at what Wikipedia had to say. Okay, then we looked at the data sheet, and now we're looking at your textbook's description. I'm going to go back to the previous slide here. what are sort of the major subsystems? We have our clock generator, we have our transmitter, we have our receiver, and then we have all these configuration registers. So there are sort of four major pieces: the clock, the transmitter, receiver, and then the configuration registers. Okay. All right. Clock, the transmitter, the receiver, and then the control and status unit, which has those various registers. Okay. And what's the game here? What we want to be able to do is take a letter, send it into the transmit unit, and then it gets shifted out through a shift register, and it becomes a bit stream that's sent out over the transmit line. And all that's done according to an agreed upon serial communication protocol. And when we say agreed upon, it means that this device is going to be connected to a receiving device. And here we're just looking at transmit with a single wire. Of course, you have to have your ground. Let me draw that. Let me do that right. The ground is always a black wire. Okay. You have to, if you just have one wire all by itself, then unless there happens to be a physical metal to metal connection between the devices, then it won't work. You have to connect the grounds. But these two devices both have to agree on this protocol, right? We have to agree number of ASCII data bits, number of stop bits, whether we're using a parity bit, and then the data rate in bits per second, which we call the baud rate. So what's the basic idea? How do we do it all? What are the steps? Well, first thing we're going to do is we're going to enable the UART, wake it up, enable it to function. And you know, the device has many peripherals on it, and the more peripherals that we enable, the more transistors are going to be switching on and off inside it. You can think about it that way. And the more current it's going to draw, and the more power it's going to consume. And so when you first turn on one of these devices, like the Mega 328P, many of the peripherals by default are powered down. When you enable it, you'll wake it up and it'll start to consume power. So the first thing we do is we'll enable it. Then we're going to configure various registers, and we're going to get into these control and status registers, and we're going to configure those, program those to set the agreed upon protocol, data bits, stop bits, and so forth. Then we're going to configure something called the UBRR here, right? And that's going to set up our baud rate for us. So we'll configure the UBRR to set the baud rate in bits per second. Now, once we've done those three things, we've activated the device and we've set the protocol. We're now going to load a character byte to be transmitted, whatever that is. We're going to load that into the UDR. That's the UART data register. And we're going to do that when that register is ready. Now, when I say, let me sort of be careful and say that again. This register can be used for transmitting. It can be used for receiving. And what it's doing is it's on transmit, it's taking a parallel word and it's sending it out through a shift register as a serial bit stream. When it's receiving, it's taking a serial bit stream and converting that into a parallel word. So what's going to be important, we're going to wait until that register is ready. We're going to poll that register. We're going to keep asking, are you ready? Are you ready? Are you ready? Are you ready? And when it says, yes, I'm ready to receive a new character, we will then load our character byte into it and it'll get sent out. And then we will just take that function and then we will repeat that for as many characters as we want to send. Okay. And what will happen is internally, the UDR, that register, will shift the bits of the byte out one by one, and it'll transmit them according to the agreed upon protocol. So that's the basic idea here. Now let's get into how we actually configure this. Now this is a whole lot of detail, and we're really only going to be needing about 10% of all the detail here, but it's going to be the important 10%. What I'm showing you on this slide are the definitions of the three status and control unit registers. So you'll see they're called UCSRA, UCSRB, and UCSRC. So let's take a look over here. These are figures that come right out of the textbook, by the way, and they're also in the data sheet. So UCSR0A, that stands for UART control and status register 0A. Now, why is it 0? That comes from the data sheet. Your ATmega 328P has one UART device in it, and it's referred to as number 0. If it had 3, they would be referred to as 0, 1, and 2. The standard way that they write these data sheets is to count them starting with 0. So that's what the purpose of that 0 is there. Okay, so we have UCSR0A. We also have UCSR0B. That's USART control and status register 0B. And then we have 0C. Okay, now I'm just going to don't memorize this. Don't even worry if the details just sort of go right over your head at this point. I want to just give you a flavor of this. So I'm just going to, just attend to this quite lightly. I'll walk you through in detail in just a bit. The things that are important here, if we want to transmit, we have to first enable the transmitter. So that means that we have to set bit 3 in this register high. See what that says? To enable the USART transmitter, you should set this bit to 1. So that's bit 3, 0, 1, 2, 3. What we would want to do is put a 1 in that bit position. Okay, and we know how to do that. That means we're going to have to get this register. It's called UCSR0B, and I want to put a 1 in that bit position. So I'll make it OR equals 1 shift left 3. Right? Or I can also write 1 shift left TXEN 0, right? Because that's one of those predefined symbolic constants. If you don't get that, don't worry about it now, because we're going to come back to it. That's just one of the many things you have to set up. Okay, all the way over to the right, we have to actually select the mode here. There are many different modes. It can be synchronous and it can be asynchronous mode. Well, the only thing we're going to be interested in is asynchronous mode. And to do that, there are a couple of bits that we have to set to 0. Now, the default is that these bits are already set to 0. So it turns out we don't have to do anything at all to set this. There's the parity mode. Are we going to be doing parity checking, error checking? We want that to be disabled, and that's 0. A couple of bits are set as 0 zeros. Nothing for us to even do there. Okay, stop bits. We're only going to want 1 stop bit instead of 2 for our purposes. So that means there's a particular bit that has to get set as 0. It'll come up as 0 by default. Okay. Other things here, we have to set the character size, how many bits, and we're always going to want 8-bit ASCII. Okay. I mentioned before that we have to look and see whether the data register is ready or not. And so there's a bit here that we're going to have to be polling. We're going to have to keep looking at that register until that bit goes high. That'll tell us that this data register is not busy. So I'm just kind of walking you through some of this kind of stuff. I'm going to show you in more detail and with actual code how you do this. The reason why I'm walking you through this is, I'm going to give you the routines for everything that we're going to need in the course. But there may come a time beyond this class where you need to get in and configure one of these things differently from the way we're using it. And so to do that, you'll need to dig into these data sheets and roll up your sleeves and figure this stuff out. Okay, let me just go to the next slide and talk about how to set the baud rate. And that's this device down here that's circled. Okay, so we have the UART clock, the clock divider, and UBRR. And so to walk you through this, let's start with this situation. Typical baud rates are going to be, let's say, 1200 to 19,200 bits per second. We can go higher. We're going to kind of keep things simple. We're always going to use 9600 baud here, but the system has there's a CPU clock, the clock at which the microcontroller is actually clocked, and that's set by the external crystal. In the case of the Arduino UNO, there's a physical crystal on that board, and it runs at 16 megahertz. 16 million clocks per second. And what we want to do here is set up a baud rate as part of our protocol of somewhere between 1200 and 19,200 bits per second. So we have to implement a divide down counter, right? We have to take that system clock, which is counting at 16 million clocks per second, and we have to divide that down to 1200 or 19,200, right? And so if we wanted to get down to 1200, what we would have to do is divide it by 13,333. And if we wanted to get to 19,200, we have to divide it by 833. So the question is, how do we do this? How do we actually take that clock and divide that in hardware by a number like this? Well, if you think back to your ECE 124 experience when you were dealing with logic design, you knew how to make ring counters, right? So what we would have to do is make a counter that's going to, let's say, count up to 833 and then back to 0. Or we count from 0 up to 13,333 and then back to 0, right? And we would clock that with our 16 megahertz clock. That's one way of doing this. And something similar to that is done inside the guts of this. And what actually happens is there's something called a pre-scaling down counter, which is what I just described. It's a ring counter that'll count up to a certain value and then it'll roll over again back to 0. Count up to a certain value and roll over again. And that essentially functions as a clock divider. How high will it count up? Well, it counts up to a value set by the UBRR. That's a value that we load in there, and that will specify what kind of a clock division we're going to get. Okay. Now then, coming out of that, the clock further gets divided by 2 and then by 4, and then it can get further divided by 2 again. An awful lot of detail there. Punchline behind all of this, 2 punchlines. First this one and then the main one, okay? Coming out of that prescaler, coming out of there, our clock is going to be our system clock, that's our 16 megahertz, divided by quantity UBRR plus 1. And so we'll know the baud rate we want, and that'll correspond to UBRR. But we see that we have these subsequent dividers, divided by 2 and divided by 4 and so forth. Okay. If I boil all of that down, it comes down to this formula right here. So the baud rate is going to be set by our clock, our 16 megahertz clock, and or whatever clock we've got on our chip, 16 megahertz in the case of the Arduino UNO. Divide that by 16, and then further divide by UBRR plus 1. So we specify UBRR to get a certain baud rate. Okay, and so just some examples here. What value UBRR do we need to get these different baud rates, right? And I've got values A, B, C, and D here. So let's suppose that we want a baud rate of 1,200 characters per second. Okay, this is the formula I just showed you. And if we take and we invert that, right, it tells us that the value we want to put into that register, right, into the UART baud rate register, is our oscillator frequency for our board or our chip, divided by 16, divided by the baud rate, and then we subtract 1. So if I want 1,200 bits per second, what comes out of that math is I would have to set UBRR with 832.33, right? I can't do a third of a clock. So I would use 832. So I would load the decimal value 832 into that register. That corresponds to 340 in hex. So I could load this value in hexadecimal into UBRR. If I wanted 9600 baud, I'll just show you that example. All right. So if I wanted 9600 baud, then I would have to load 103 into there, which is 67 in hex, which is 0067, 0x0067 specified in hexadecimal. Now the thing about all these numbers here is these all correspond to 16 bits of information, because you see it's 0x followed by 4 hexadecimal digits, right? We have 0340. So it takes each hex digit corresponds to 4 bits. So what this tells us is that we need to have a 16-bit register here. Now, in order to accommodate values here that are that are as wide as shown here. We have an 8-bit machine here, right? And so how do we handle a 16-bit value? What actually happens is there are 2 registers in the UBRR. There's the UART baud rate register high and the UART baud rate register low. And the upper 2 hex digits go into the high, and then the lower 2 go into the low. Okay. Now, for everything we're going to do, we're going to be using 9600 baud to make this simple. So what we want in our UBRR is just 0x0067, right? And that corresponds to line C here. And so to do that, we would load in 00 into the UBRR high register, and then we would load in 0x67 into the low register, right? And 67 in hexadecimal corresponds to 103 in decimal. Now, it turns out that the default value here, when you power this thing up or reset it, it's going to set UBRRH to 0, right? So the default value is already 0, so we don't have to set that, okay? Now, I realize I'm throwing this stuff at you fast via PowerPoint. I'm just going to show you a kind of a cookbook recipe for how to put all this thing together, right? So how do we configure everything to get the common protocol we're going to be using always in the course? So we want to configure our USART to operate in UART mode for asynchronous serial communication, 8 bits, 1 stop bit, no parity checking, 9600 bits per second. All right. So the first thing we're going to do is we're going to enable step 1. We're going to enable that bit 3 of the USCR0B register. That's the UART control and status register 0B. We'll enable that bit. The next thing we're going to do is we're going to set our configuration, our protocol, and a number of stop bits, and our baud rate. Right. We're going to set those by putting a couple of 1s in the right place. So I'm going to show you the actual code you need to do that. That's step 2. Okay, step 3 is sort of the tricky part. We have to keep polling. We have to keep querying this register here. All right. This is UCSR0A. We have to keep looking at that register until this particular bit 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, until bit 5, which is called UDRE0, until that becomes 1. We keep waiting until that bit becomes 1. And that tells us that the transmit data buffer is empty and ready for us to receive a character. And then once that's done, we're going to be able to send a character out. Okay, so now let's take all of this and let's just map this onto some code. Okay, step 1, set the transmit enable bit. All right, so we just do this line here. That will enable the transmitter. There it is. Okay, the next step, we want to set our protocol, our configuration bits, and our baud rate. And these lines of code will do that. These will give us, they'll program it to operate as an asynchronous mode, meaning we don't have to share a clock between transmitter and receiver. 8 bits of data, 1 stop bit, no parity checking, right? And then we'll divide the 16 megahertz clock down to give us 9600 bits per second. So you can use this code here to do this. Now, one subtlety about this. This will only work, we want it to give us 9600 bits per second, and this will only work if we have a 16 megahertz clock. When you get a brand new Atmega chip fresh from the factory, it actually runs with an internal 1 megahertz clock. So you would have to change this if you wanted it to work for that clock rate. So if you're running your Atmega 328P with a different clock, you would have to change the UBRR0L. When you need to know about that, I will let you know. I just want you to know of the existence of this problem right now. Okay, then we get sort of the tricky part. We have to wait until the transmit buffer is empty. That meant that we're looking at a particular bit, right? This bit here, and we're waiting for it to go high. So how do we just examine that bit? We look at this whole register, and then we AND it with a mask with a 1 in that bit position, right? And we wait for it to go high. So while it's equal to 0, we're just sitting. Now look at this construct. We have a while, right? It's a while loop, and the only statement in the while loop is a null character, right? This deceptively simple line, what it will do is it'll just sit there and wait. Just sit there and wait until UDRE 0 goes from 0 to 1. Okay, all right. It's deceptively simple. Let me show you sort of a different example of this altogether. Suppose I wrote this. We know that we've been working with this super loop for a long time, right? Or for a few weeks, I should say. Let's say port D, port B, XOR equal 1, shift left. Okay, we've done a command like this for a while, right? This will toggle the internal LED, right? This construct, a while 1 is always true, toggle that LED. Suppose I just did this, while 1 semicolon. That is equivalent to while 1 open brace semicolon close brace. It's a null statement. It doesn't do anything. Each of these represents an infinite loop, right? 1 is always true. A semicolon is a null statement. It doesn't do anything, right? It's a valid statement. So each of those represents an infinite loop. What we've got here is not an infinite loop, but it's a loop that'll just sit there and wait and wait and wait and wait until this bit goes high. So this is called polling. We're polling or checking the status of that bit, of the UDRE 0 bit of the UCSR0A register. And we're waiting for that to go high. And when it goes high, we'll get out of this loop and we can move on to the next step. And all this is doing is holding up the processor until it tells us that transmit data buffer is empty. There's no character that's currently in there being shifted out. Once it's empty, we can then go ahead and send a character, and the way we do that is we just load whatever character we want into our UART data register. Okay. Finally, let me take this and put that into some code. So here's a program, and I'm going to end this class with this. But this is how we're going to start the next class also. So we're going to write a simple C program for the Atmega 328P on the Arduino UNO to transfer the letter G serially. And I just got this from your textbook, this example. Transmit the letter G serially at 9600 baud continuously with half-second delay between transmissions. Here's the protocol we want to use: 8-bit data, 1-stop bit, no parity bits. So what we're going to be doing is configuring the transmit side, and on the receive side, we're going to have to hook up. We're going to have to configure our serial terminal emulator to match that protocol. And we want to do sort of four versions of this. First, just write all the code in a single main function. Simple enough. Then I want to reorganize it into 3 functions. One function which will initialize the UART baud rate and set the protocol, and another function that will send the character. Then I want to do a revision where instead of just sending the letter G, it'll write wow. And then I want to modify it where instead of just sending a few letters, it will send a string of text. And in this particular case, shall I compare thee to a summer's day, borrowing from Shakespeare. Okay, so I'm going to show you on the next slide the first version of this, right? Which is it's just the code instance, in code, in our editor of what I just showed you here. All right, and then we'll walk through that in our next class, and we'll build all these other parts. So there's the code. This is called serial no functions, and the reason why I call it that is going forward, when you use the peripheral, what you're going to want to do is put the the sort of the gnarly bits of code, these detailed codes, tuck them away into a function instead of cluttering up main with all this kind of stuff. It really belongs in a function, and you'll see what I mean by that when we go through this exercise, parts A, B, C, and D. But the first version of this, okay, so serial, no functions. This program continuously sends the letter G to the serial monitor via the UART on the Atmega 328P. Okay, now it's a simple code. I had a different version of this that I showed last year in 231 when we were using the MPLabX code. And the revision history is mostly for me. It helps me keep track of any changes that I'm making to it. But what's happening in the code? The very first thing we do is we initialize the UART. By that, we mean we enable it, we set the protocol, and we set the data rate, the baud rate. Then we have our while loop, and we know that that while loop is just going to keep running over and over again. So we're going to keep doing this. Now within that, we have this while loop, and we're just waiting until that transmit buffer is empty. And that's the point I just sort of elaborated on previously. We're waiting until this goes high. And we're just going to stay there until that goes high. And it will go high when there's nothing that's in the transmit buffer being shifted out, right? Once that goes high, we're going to send the letter G. We're going to put letter G in that UART data register. And it's going to go and start shifting that out a bit at a time at 9,600 bits per second, right? And then the loop will come back to this while statement, and it'll wait until it's done shifting that data out. And when it's done, it'll send out G again. So once you've got this running on your host computer, you're just going to see a bunch of G's, right, show up. And we'll pick it up there next time. Continuing with this code here, show you the demo, and we'll also go and look at parts A, B, C, and D. So with that, we're done for today.